Hello everyone. Quantum non-locality is often described as a real physical process supported by irrefutable evidence. However, this assessment is about to change, and I would like to explain what is going on. First of all, what is locality? In plain language, this is one aspect of a broader principle, which is the presumption of no miracles in physics. For example, if we have two systems, A and B, then a change in A cannot produce a change in B unless there is a direct mechanical connection between them. System A causes a change in system B by exerting a physical, not metaphysical leverage. In contrast, if we have two isolated systems A and B, and they manage to influence each other without mechanical interaction, then we have a miracle. The name of this miracle is non-locality. In quantum mechanics, correlated systems are described as non-locally entangled if they are believed to have this magical ability. So, let us ask an important question. Why do physicists believe in non-locality? Is it because there is evidence for it? Surprisingly, the answer is no. When we look at the reasons for questioning the concept of locality, we find a remarkable gap in our understanding. Indeed, we have a famous argument known as Bell's theorem, and it shows that quantum properties cannot be expressed by local phenomena. However, this argument only holds for properties that are jointly distributed. In other words, Bell's inequality only applies to properties that exist at the same time or behave as if they exist at the same time. You see, if we denote the totality of local processes by a circle, then Bell's inequality only holds on this side where we have compatible observables. However, quantum theory predicts Bell violations with properties that are mutually exclusive. Therefore, they cannot be simultaneous. So quantum predictions are located on this side. To be clear, I wish to emphasize, we have local behavior on both sides of this circle, yet Bell's inequality only holds for this side. So, proverbially speaking, Bell compared apples with oranges. Now, you might say, wait a minute. If the distinction is so clear, then why do we have this problem? The answer is that we did not know how to avoid it for a very long time. You see, in theory, we should be able to achieve local behavior with properties that exist at the same time and with properties that do not. So, Bell's inequality should not matter for discussions about locality. Unfortunately, in practice, the second mechanism seems impossible. No matter how many times we try, we keep getting to the same conclusion. Local properties behave as if they exist at the same time. Allow me to explain. When we have only two variables, we can determine if they are correlated or not, but we cannot determine why this is happening. Maybe they influence each other directly, or maybe they are both influenced by some other common cause. In contrast, if we consider several properties at the same time, then we have several coefficients of correlation, and we can identify different patterns of combination. Bell-type inequalities are derived by using special rules for adding and subtracting such coefficients. For example, if we have four suitable pairs of variables, then we can use the so-called CHSH protocol. Let us take a closer look at this set of four observables. We are interested to see what happens if we measure them two at a time. A with B, B with C, C with D, and finally D with A. As you can see, we have a chain that closes on itself, and this is where the difficulties begin. The concept of locality entails that isolated properties do not influence each other. This has a straightforward statistical implication. In a chain of pairwise measurements, we must always have pairwise consistency. In other words, measurement outcomes do not depend on remote conditions. Therefore, if we look at observable A, then we expect the same value of A in combinations dA and AB. If we look at B, it must have the same value in AB and BC, and so on until the chain closes back on itself. If we take some time to think about this, it becomes clear that we can only expect compatible correlations as if all the properties exist at the same time. You see, it does not matter if we actually make the measurements at the same time or not. The apparent problem is that we can only get pairwise consistency if these values are compatible with each other, or else the chain cannot be closed. To use more technical terms, our variables need to be jointly distributed. Let us make a quick review of what we have just seen. We need to have pairwise consistency in order to verify that we have locality. Yet, if we want to have pairwise consistency, then we cannot avoid the appearance of simultaneity. Therefore, Bell's inequality should apply to every local process. We can illustrate this with a straightforward example. In this type of experiments, the goal is to obtain 4 coefficients of correlation and to put them together according to this rule. Let us see what happens if our properties are uncorrelated. This means that all the coefficients are equal to 0. So 0 plus 0 plus 0 minus 0 equals 0. Yet quantum theory predicts a sum that is larger than 2. So if we want to explain quantum entanglement with local mechanics, we need to have strong correlations. Yet, look what happens when we combine strong correlations and locality. If the value of A is plus, then B is also plus. Yet the value of B has to be consistent in both combinations, so C is also plus, or else we do not have strong correlations. Furthermore, C is also expected to be consistent, and the same holds for D. Therefore, all of our measurement outcomes should be the same. They should all have plus values, or else they should all have minus values. This means that we have no freedom in how we combine the possible outcomes. As a result, we get 4 compatible correlations, and our sum becomes 1 plus 1 plus 1 minus 1, which gives 2. Obviously, this is not good enough. Our goal is to achieve something larger than 2. So, how can we make this happen? From a mathematical point of view, the answer is straightforward. We need the 4th coefficient to be negative. For example, imagine that we can somehow get a coefficient of minus 1 here. The sum becomes 1 plus 1 plus 1 minus minus 1 with a total of 4. Easy, right? Well, not so fast. Let us look at our chain of measurements again. To get the first strong correlation, we need to have a plus value for A and a plus value for B. To get the second strong correlation, we need a plus for B and a plus for C. Finally, to have the third correlation, we need a plus value for C and another for D. As you can see, after defining just 3 correlations, we have already covered all the bases. We determine the value of 4 variables, meaning that the final coefficient of correlation is automatically fixed as well. In this case, it can only be positive. Anything else is logically impossible. Yet, we need to have an anti-correlation here, or else we cannot explain quantum behavior. In other words, if we want anti-correlation between these pairs, we cannot have pairwise consistency. The only way to introduce an inconsistency in this mixture is if the value of A changes between measurements. For example, detector A must show a plus if B is plus, and it must switch to minus if D is plus, even though D and B will always show the same value. So, we are forced to consider non-local scenarios. Detector A must know which of the variables is chosen for coincident observation and produce measurement outcomes accordingly. In short, it looks like we need a miracle. To sum up, this is our conundrum. In theory, it should be possible to have sequential properties that are pairwise consistent and mutually exclusive at the same time. In other words, we should have local behavior on this side of the circle as well as on this side. In practice, however, we cannot achieve the necessary combinations because they seem to be impossible. Remember, we said that Bell's inequality compares apples with oranges. We have an argument about simultaneous properties, but quantum theory predicts violations with sequential properties. So Bell's inequality should not matter for quantum entanglement. Nonetheless, it appears that sequential properties must also behave as if they are simultaneous when they are local. Therefore, when we get Bell violations with sequential properties, the standard interpretation is that we have direct influences between our properties. Intuitively, this assumption feels wrong, but for a long time we simply did not know how to avoid it. Yet, now that we understand the problem, allow me to show you the solution. Quantum theory predicts Bell violations for properties that are mutually exclusive. For example, when the arrow of an analog clock points at 12 o'clock, it is not pointing at any other time marker. 1 hour later, it will point at 1 o'clock, and so on. Hence, we have properties that exist only one at a time. The question is, how can we measure together two properties that cannot exist together? Yes, we can make two copies and look at the coincidence between synchronized clocks. However, this is not really a solution. If our clocks are truly synchronized, then different observables are still not possible at the same time. Both clocks show 12 o'clock now, and both of them will show 1 o'clock later. We can probably change the time on the second clock by hand, but then we are likely to distort the very process that we are trying to understand. You see, if we want to get to the essence of this process, then we need to find a way to measure sequential properties without interfering with our systems. As it turns out, the best way to understand this mechanism is by studying relationships that can happen as part of a single system. Hence, if we cannot measure our variables at the same time, then we have to measure them as they happen in sequence. Instead of simultaneous properties, we define an extended time interval as a window of coincidence. However, our interval should be just long enough to include two properties at the most. This is important because we do not want to measure all the properties at the same time. As we have just seen, Bell's inequality cannot be violated if all the properties are recorded at the same time. Instead, we have to consider events that are mutually exclusive and only become relevant in pairs, two at a time. So let us see what happens in this case. If we look at our typical setup for a Bell experiment, we have 4 binary variables. Each observable can have a plus or a minus value, but all of them can only happen one at a time in sequence. Let us try to visualize a possible realization of this mechanism. First, we register a plus value for A, then we register a plus value for B. In this window of observation, we have one pairwise coincidence. Then, property C becomes real, also with a plus value. so we get another pairwise coincidence. Finally, it is time for D to become real, and we have recorded 4 events. However, we are not done yet because we still have more values to consider. Hence, the next value after D+ is not another A+. We are now moving forward in time, and we can expect a different value. So, the window of measurement between D and A contains a plus and a minus. After this, we continue recording pairs of events around the circle, just like before, B, C, until we get to D-. Finally, at this point, we can close the cycle back at A+. As you can see, when we have sequential properties, we do not have parallel blocks of events. Instead, we have a single sequence of events that follow a continuous path. This is easier to understand if we recall the properties of a Mobius strip. In this case, if we follow a continuous trajectory, we need to go twice around the circle before we return to the chosen starting point. The question is, do we still have locality in this case? As you remember, the statistical marker for locality is pairwise consistency. Any measurement outcome should be the same in any pair of combinations. In this case, we have a linear sequence of events where every event happens only once between 2 other events. For example, B is right here between A and C. C is only registered once between B and D, and so on for all the variables. In short, we get pairwise consistency by default. Every event is used twice in 2 different combinations. Moreover, we have the same double cycle over and over, and we can repeat it as many times as we want to accumulate a large sample for statistical significance. The best part is that we have a simple pattern that is easy to analyze. As you can see, A and B events always follow each other with identical values. The only possible pairings are plus or minus. Therefore, our coefficient of correlation is +1. If we look at the combinations between B and C, we get the same pattern. The coefficient of correlation is +1, and the same is true for the pairing of C with D. However, we have a double crossover between observables D and A. This means that we can only get coincidences between +- or minus+ events. In other words, we get perfect anti-correlation. Therefore, the coefficient of correlation is -1. If we plug these numbers into the CH-SH inequality, we obtain a result that is much larger than 2. Therefore, we can violate a Bell-type inequality even though we have pairwise consistency. Let us recall that local behavior can manifest in 2 ways. We can have it with simultaneous properties and with sequential properties. We knew that Bell's inequality applies to jointly distributed variables and did not extend to mutually exclusive properties. However, we did not know how to describe local behavior without regressing back to simultaneous properties. Fortunately, now we do, and everything finally falls into place. Sequential properties can still be local if we analyze them with adequate procedures. At this point, you might ask, what about all the previous evidence to the contrary? Don't we have overwhelming evidence for quantum non-locality? The correct answer is no. We have good evidence that quantum theory is correct, but the label of non-locality was added for interpretive reasons. Indeed, if we pay close attention to the relevant concepts, we can see that quantum theory does not require non-local interactions even when we have entangled systems. Let us recall that quantum correlations do not allow for superluminal communication. This is known as the no-signaling principle. For example, In a typical Bell experiment, we have two observers, Alice and Bob, and each of them has a choice between two observables. Alice's settings alternate between A1 and A2, while Bob's settings alternate between B1 and B2. The no-signaling principle is captured in this expression. In other words, the probability of measurement outcome A1, given that Alice has chosen to measure A1, does not depend on Bob's decision to choose between B1 or B2. This is a more precise way of saying that Bob cannot send signals to Alice by switching his measurement choices. Yet this relationship cannot just hold for one observable. It has to hold for all of them. Bob cannot signal anything to Alice, and Alice cannot signal anything to Bob. Hence, we have four similar expressions governing the outcome independence of each measurement setting. Now, let us think. What mechanisms of interaction are possible when we have no signaling? The first possibility is that all the observables are statistically and physically independent, meaning that they are not correlated. This condition is compatible with all the rules, but we are not interested in it. After all, if we have uncorrelated properties, then we cannot get Bell violations by default. Hence, this scenario is not relevant for our discussion. The second possibility is that we have strong correlations by virtue of non-local action. Yet, here we have a complication. In order to be non-signaling, the settings of Bob cannot have any influence on the events of Alice. As you can see, the probability of Alice's outcome does not depend on Bob's choice. This means that the only possible interaction is for Alice's events to influence Bob's events. In other words, Alice's events can serve as a common cause for both of Bob's settings. This would be plausible if the no-signaling principle applied to Bob and not to Alice. However, we know that this is false. The principle includes all of these conditions, meaning that it applies in equal measure to every observable. None of Alice's events can influence Bob's choices, and none of Bob's events can influence Alice's choices. More importantly, this includes any conceivable measurement choice, not just the four listed combinations. Indeed, it must also include the choice not to measure anything. Otherwise, Alice and Bob could send signals by changing the number of measurements they make, for example in settings with more than two entangled quanta. In short, this scenario is not plausible in quantum mechanics. This leaves us with the third scenario. The events of Alice and Bob are statistically dependent but physically independent. In other words, they are correlated by virtue of some prior cause, but they are not able to influence each other directly. This is also known as conditional independence from a statistical point of view. It should be easy to notice that in this case, the no-signaling condition has been reduced to the locality criterion. After all, this expression captures the famous principle of separability between local observables given the effect of hidden variables. Yet, this means that quantum behavior can only be interpreted in a meaningful way if it is local. For those who are interested, there is a treatise on this topic written by Paul Raymond Robichaud. The main conclusion of this dissertation is that no signaling and locality are equivalent in any physical theory with invertible dynamics. Notably, this also includes quantum mechanics. Why is this important? The answer is very straightforward. In modern physics, simultaneous properties obey the CHSH inequality with S no larger than 2. Quantum theory obeys Cyril-Son's inequality with S smaller than 2.8. Yet the no-signaling condition obeys the Popescu-Roerlich inequality, which reaches all the way to 4. This means that non-signaling correlations exceed the domain of quantum phenomena. We can even display the so-called superquantum correlations. In other words, we cannot ever expect to find quantum correlations that are signaling, assuming fair play. Yet, we have just seen that the no-signaling criterion is formally equivalent to the locality criterion in relevant physical contexts. Therefore, local correlations also expand beyond the scope of quantum entanglement. Indeed, I have shown you a few minutes ago that the locality criterion produces correlations up to s equals 4, just like the no-signaling criterion. Ergo, we cannot use quantum behavior to falsify the principle of locality. In short, quantum theory is local. Despite this conclusion, some of you might still say, wait a minute, what about Bell's theorem? Didn't Bell demonstrate the contradiction between local behavior and quantum behavior? The correct answer is no, he did not. To be more precise, Bell claimed that he did, but he skipped an important nuance in his analysis. Let us take a closer look at the notorious paper on the Einstein-Podolsky-Rosen paradox. As you can see in this image, Bell defined the locality criterion in expression 2 in terms of conditional statistical independence. This is the same condition that I described above in terms of pairwise consistency. So far, so good. Bell continued to use this criterion consistently throughout his paper. However, he performed his analysis exclusively in terms of two variables. This is important because he needed to use more than two variables in order to complete his argument. Indeed, in his definitive chapter 4, Bell introduced a third variable and promptly derived his famous inequality in expression 15. Yet there is a nuance here. You see, when we have three variables with pairwise measurements, we need to make three joint measurements: the coincidence between A and B, or between B and C, or between C and A. At no point do we have to measure all the properties at the same time. Therefore, we do not need to assume that they are all real at the same time. With entangled pairs of quanta, only two properties become expressed at a time. And yet, Bell derived his inequality by treating the three variables as if they are jointly distributed. In other words, his proof is not based on the locality criterion for each pairwise combination. Again, the locality condition is only defined for two variables in this case, because we only measure two properties at a time with entangled quanta. This results in these three expressions. Instead, Bell used a condition that treats all the observables as simultaneously real. Please note, this expression necessarily entails the three pairwise conditions. This is self-evident. However, the reverse is not true. Indeed, it is possible for all of these three conditions to apply, while the global separability condition does not hold. This is why we were able to achieve Bell violations with classical observables. So, what is the physical significance of this unstated criterion in Bell's theorem? If we keep thinking in terms of pairwise measurements, we can see that it compresses two conditions. Number one, all the measurements are local. Number two, all the properties are real at the same time. As we have seen above, the first condition does not obey the inequality. It leads to quantum and superquantum correlations. In contrast, the second condition imposes measurable restrictions on the possible coefficients of correlation. Therefore, condition number 2 is the reason for Bell's inequality. To sum up, Bell did not prove a contradiction between quantum theory and locality. He proved a contradiction between quantum theory and simultaneity given special conditions. To be more precise, he confirmed the claims of quantum theory that non-commuting variables are mutually exclusive. If we detect Bell violations, then we are measuring properties that cannot be real at the same time. It might be helpful to get a historical perspective on this concept. The best way to explain the source of this problem is by using a simple example. Sometimes, measurement outcomes are predicted by doing what is known as vector decomposition. For example, a diagonally polarized beam can be expressed as the vector sum of a vertical and a horizontal component. Accordingly, if we make a vertical measurement with a polarizing device, we can predict how much of the input projection will be transmitted by estimating the magnitude of the corresponding component. Yet, now we can look at this output beam and ask, where did it come from? Or, more to the point, what happens during the so-called preparation stage? Traditionally, this problem was analyzed in terms of the so-called component vector realism. In other words, we assume that the source had a hidden slice with vertical polarization. This component went unperturbed through the polarizer, while all the other components were blocked. An alternative interpretation would be to assume that the input beam was in fact diagonally polarized, and that all the possible virtual components are nothing but mathematical abstractions. In this case, we can say that the input beam was rotated by the polarizer proportional to the amount of energy that was available for this plane of oscillation. In other words, we can interpret this vertical output as a contextual property. When quantum mechanics was discovered, it became apparent that output projections are contextual, but the details of this process were very hard to interpret. And so, the famous solution of Bohr was to keep the idea that preparation does nothing. Instead, he argued that the act of observation has a creative retroactive effect. In other words, the beam is still described as if it contains many superposed components. Moreover, it is not affected by the polarizer in any consequential manner. Instead, every photon remains in a superposition of passing or not passing through the filter until the act of detection forces it to collapse into a well-defined state. This is a complicated topic, and we do not have time to discuss it here in depth. The important aspect for our discussion is that Einstein, Podolsky, and Rosen reacted to Bohr's metaphysics with the famous counter-argument. In particular, they noted that non-commuting quantum properties can be investigated with entangled systems, leading to a very strange conundrum. Non-commuting properties are mutually exclusive according to quantum theory. Unfortunately, if we assume that measurements create reality, then we are left with two unacceptable alternatives. Either quantum theory is wrong, or it is non-local. As you can see, it looks as though we have a contradiction between local realism and quantum theory. In actuality, these concepts have a very narrow meaning. If we assume that measurements always create quantum properties, then we cannot explain predictable observations. In particular, in the special case of quantum entanglement, we have to assume that some other measurement conducted far away produces non-local effects. In other words, we end up with magical conclusions, but only because we started this analysis with magical assumptions. The logical alternative to this result is to suppose that quantum theory is wrong and that non-commuting properties are real at the same time. Again, this alternative only seems needed if we accept the Copenhagen interpretation. As you can see, the concept of local realism, as used in quantum mechanics, has nothing to do with local realism in the wider sense. It only describes what is left over, so to speak, if we assume that measurements create reality. Insofar as it means anything concrete that we can express mathematically, it only includes the properties that exist at the same time or behave as if they exist at the same time. In short, Local realism means simultaneous realism in this analytical context. It cannot include all the local properties because sequential properties are also local, as we now know. Coming back to the main thread of our discussion, we see that Bell's theorem was an argument about local realism, but only in this narrow sense inherited by tradition. The relevant question was about non-commuting variables. Do they exist at the same time or not? Bell found a way to answer this question experimentally, and as a result, we know that some quantum properties are indeed mutually exclusive. More importantly, Bell did not prove that quantum theory was non-local. His inequality only holds for simultaneous physical qualities. The problem is that Bell did not seem to know this, and he managed to convince his followers that quantum theory is non-local, rather than the Copenhagen interpretation. In conclusion, quantum theory predicts violations of Bell's inequality. These violations tell us that non-commuting properties exist only one at a time. Yet, this has nothing to do with the concept of locality as commonly understood. Unfortunately, it was hard to falsify the concept of non-locality because of a theoretical problem. We did not know the rules of combination between sequential properties. The unexpected solution was to fit such properties on a Mobius strip, finally proving the equivalence between non-signaling and local properties. Concerning the bigger picture, the main conclusion is that quantum behavior is contextual, but measurements do not create reality. Quantum theory is correct, as insisted by Bohr, and quantum theory is incomplete, as shown by Einstein. The two sides can find common ground if we just stop looking for miracles in quantum physics.